So in this section we will see the local minima in the deep networks. So local minima are called as the local minima are called so because this value of the loss function is minimum at that point in a local region. So local minima is called as local minima because the value of loss function is minimum when we are talking about it at the local region. So the global minima is called global. So the value of the loss function is minimum and globally it is having the entire domain the loss function. So local minima and global minima both are the important part in the neural network training. So when we are talking about local and global, so first we should know what is neural network. That is nothing but the collection of various neurons with number of layers. So local minima is a significant obstacle we can say for the successful training because the local minima is dealing with the complex input and output relations actually. So we can say that the local minima is a particular point where the value of loss function is in the local region and the global minima is a point that is having the domain loss function that is also a minimum. So local minimum are called since the value of loss function is minimum at the local region and global minimum is having the value global at the entire domain of the loss function. So rearranging neurons in a layer of neural network for this local and global minima. So first we should know that whenever we are having the particular neural network, is it necessary to often slide down the local minima or we have to know about the global minima? So it is reasonable that we should assume the global minima represents the optimal solution and local minima are problematic. So the global minima is very widely used. So the rearrangement of neurons in a layer of neural network. So the rearrangement of neurons in the layer contains the input neurons, output neurons. So the input neurons are nothing but the number of features your neural network uses for making the predictions. The input vector needs one input neuron per feature. Then comes the output neuron. This is the number of predictions we want to make. So for the regression task, we can have one value per task. And for the binary classification, we can use one output neuron per positive class, whereas the output represents the probability of positive classes. That means in input neuron, we can take one input neuron per feature and in output neuron we can take one neuron per positive class. So that is how we can rearrange the input output neurons. Then comes the hidden layers and the neurons as per the hidden layers when we are talking about the rearrangement. So the number of hidden layers is highly dependent on the problem and the architecture of your neural network. Yes, we have seen in the last section that the total number of hidden layers are according to the complexity of our neural network. So the number of hidden layers are highly dependent on the problem and the architecture of our neural network. So generally 1 to 5 hidden layers can serve our problem. In general, using the same number of neurons for all hidden layers will suffice. Means generally when we are not having a very large complex problem, at that time the same number of neurons for hidden layers can be okay. For some datasets, having large first layer and following up the small layers will lead the better performance. Means when we are starting with the neural network, so the small layer starting with large first layer and then connecting it with the smallest layer can give us the better performance. So in this way we can rearrange the neurons in the layer of neural network. Now we have seen the local and global minima. Now the spurious local minima in the deep networks. So the maximum likelihood estimation in the finite mixture of distribution setting is an ill-posed problem that is treatable through the EM algorithm. As we have said that the local minima is problematic and the global minima is very useful, but the spurious local minima is used when we are having a maximum likelihood estimation. So the existence of spurious solution, that is the singularities and non interesting local maximizers, makes it difficult to find a sensible mixture fits for non-expert practitioners. So whenever we are having the unsupervised data, unsupervised learning, at that time this spurious local minima in deep network plays the good role, because they are responsible for making and finding the sensible mixture fit, so that though we are having the unsupervised learning method, but still they identify the perfect fit with the local maximiers. So by a concentration of measure argument, this implies that in a high input dimension, all the target networks of relevant size lead to the spurious local minima. So we can say that the by the measure argument, if we are having the highest input dimension, then almost all the target networks can be covered. So when we are referring to the local minima of function f on the Euclidean space, we always have a mean spurious local minima. That means when we are referring the local minima on the Euclidean space, keep in mind we can always have the mean spurious local minima, where all the neighborhood of the particular W is present over there. When the labels are the outputs from the teacher network of the same architect with fixed weights for the Gaussian input, there is a spurious local minimizer. So whenever we are having the labels and that labels are having the outputs, and that outputs are of the same target, that is of the fixed weight input, Gaussian input is there, then we can say that there is always a spurious local minimizer. So this is all about local minima, global minima, rearrangement of neurons in the network, and the spurious local minima in the network, deep network. Now in our next section we will see the concept of expert system and its characteristics. Thank you.